So chapter 11 is all about radicals. We haven't really covered radicals too much so far this year. So I'm going to start out with the very, very basic concepts of what makes a radical. So let's start off by comparing heterolytic cleavage. What does the prefix hetero mean? It's different, right? So in this case, it's a movement of electrons to a different atom. And so, for example, we could show this bond right here dumping electrons over to the atom X. And when we do this, will X become a cation or anion? An anion, right? Because now it will have a lone pair, negative charge. That means that Y will be our cation. And so anytime you do heterolytic cleavage, you're moving two electrons. And then you make an anion and a cation, usually. Let's compare this to homolytic cleavage. Homolytic cleavage, in this case, isn't going to dump two electrons onto one atom. It's actually going to split them between two atoms. So let's take a look at this. So we've got X and Y. And when you move one electron, you need to be very careful with your arrows. Instead of a two-headed arrow, you have a one-headed arrow, indicating one electron is moving to Y, and then the second electron is moving to X. To show this, we need X with one electron, and then Y with one electron. And this time we refer to these as radicals. Radicals are any organic compound that has unpaired electrons. So this has a single electron rather than a set of electrons. So this is always referring to a movement of individual electrons. So it is pretty different. Radicals tend to be less stable, so we don't see them as often in organic chemistry. However, they are very synthetically useful due to their instability, and we'll see this later on. But the big thing I want you guys to note that takes a while for people to get used to is that arrow notation. Anytime you see an arrow that looks like this, that means that you're referring to two electrons. And this is not the same thing as a single-headed arrow, which refers to movement of one electron. So in this chapter, make sure that you really pay attention to your arrow types and make sure that it's clear based on your arrow that you're moving one electron and not two. So let's take a look at some examples here. One type of reaction we may occasionally see is loss of a halogen. So in this case, the R groups are carbon placeholders. The X group is my halogen. And in order to show this, we're going to kick off our halogen like that. And then the second electron will go over to the carbon. And when we do this, we're going to still have our carbon group right there. One of the R groups will now go in plane and out of plane. Whoops. Or into the board and out of the board. And then X over here, we know is going to have an unpaired electron, so it's a radical. And then if we think about that carbon over here, what's its hybridization going to be if it has an electron right there?
It's actually
sp2. Be sp2, right? This is actually very similar to a carbocation. So you're going to have this p orbital sticking up and down, and this single electron can be either in that top lobe or the bottom lobe. That's the goofy nature of electrons, right? They can be on essentially both sides at the same time. And so this is a trigonal planar or sp2 intermediate. It's important to remember that it's very, very similar to the carbocation, but it does have an electron in that orbital. The nice thing with this is they follow the exact same stability trends as carbocations, so you don't have to learn anything new. So radicals follow the same stability trends as carbocations. All right, just to review, what's the most stable type of carbocation? What's even better than tertiary? Resonance. So we've got resonance as the first one. And that's even more stable than tertiary, which is more stable than secondary, which is more stable than a primary radical, which is more stable than a methyl radical. So it's pretty easy to figure out because of the similarity. But we do have to pay attention to that resonance part a bit more. And so let's practice doing some resonance with radicals. All right, so let's draw an example molecule here. And I'm going to draw all of my hydrogen atoms. And I'm going to color code them. Got green, green, green. I'll do blue over here, and I'll do red over here, just so we can keep track of them all. All right, in this example, we're going to lose one of the green hydrogen atoms. So I'll show hydrogen atom getting pulled off. Second electron goes over to that neighboring carbon. And then up here, I'll do minus H dot for loss of that radical group. Let me clean this up a bit. All right, and then we'll redraw this over here now. Carbon backbone is entirely the same. We still have the two remaining green hydrogens. We have the blue one right here, and we've got the red ones right here. And then we know we've got an electron that was left over on that carbon atom. Does that make sense? All right, so the whole idea with resonance when we were working with carbocations was to delocalize that positive charge across multiple atoms. Same idea with unpaired electrons. We want to move them around so that they're not localized on one particular atom. So one way you can do this is say, all right, this radical right here wants to form some sort of bond preferentially. So maybe it wants to dump down here, but it needs a second electron to form a bond right there. What do you think I should do? Yeah, take it from the next door pi bond. So we could take one electron from that next door pi bond. That means that there's still one electron in the system. Where do you think it's going to go? Yeah, the carbon on the far right, probably. So this resonance arrow pushing scheme requires 3 separate single-headed arrows. And now we'll show the delocalization. Oops. So now the pi bond's on this side. The single electrons right there. Got green hydrogens, blue hydrogens, and red hydrogens. And just like with any resonance structure, you want to put brackets around it. And then have a double-headed arrow indicating that it's not one or the other. It's not flipping back and forth. It's actually an average of the two here. So this would be an example of degenerate resonance structures where they're both equal contributors, right? They both look the same, just flipped over. All right, so let's practice a different one. Or actually, before we do that, I did want to get into some nomenclature. If we look at these green protons right here, does anybody remember what those are referred to as? That particular position? Close. It's allylic. Allylic protons are the protons on the carbon adjacent to a pi bond, and so that's important to know. And then up here we've got blue protons. These are attached to the carbon that has the pi bond, and these are referred to as vinylic. And occasionally I will use these terms, and in fact we'll learn a reaction about this allylic radical system later on. All right, so let's do some practice with resonance. All right, so There's two different resonance structures for this, so I'll get you started with the first one, and then you need to provide me with two more. And there's a radical on that very top carbon. So we need to fill in two other resonance structures that will work for this. So I'll give you guys a minute to work on that, and then check with your neighbor to see if you agree. All right, so let's take a look at this. The whole goal is to move that single unpaired electron around on to multiple different atoms. So maybe I'll push it this way. What else should I do?
Break that pi bond.
Yeah, break the pi bond. One electron can go up there and form a new pi bond, right? But we do have one electron left over in that pi bond that we broke, so we need to put it somewhere. So I'll dump it on that lower carbon. All right, so that's one resonance structure where we've formed a new pi bond up here. This group's still hanging off. It was untouched. And now that single electron's located on that central carbon right there. All right, we can continue pushing this single electron. So maybe I'll push one here, one electron over from that pi bond, and then the remaining electron in that pi bond will get dumped over onto that last carbon atom. And we can end up with that electron dangling off the end there. Does that make sense? So it's just like normal resonance, but quite often it has more arrows, and you need to be very, very careful to use the single-headed arrows rather than the double-headed arrows. Make sense? All right, so let's take a look at all the different reaction types. And we'll just do the elementary steps at first, and then we'll go into the more complicated ones later on. So the first one is radical cleavage. And in radical cleavage, that looks a lot like the homolytic cleavage that I just showed you. So one electron will get dumped over to Y. The second electron will go over to X. And you end up generating two different radicals. And in this case, it would be an X radical and a Y radical. And so we do need to show those single dots. So that's pretty easy to remember. The next one is radical coupling. And essentially radical coupling is the reverse of radical cleavage. So let's say we've got two radicals around, X and Y. They can pair up their unpaired electrons and form a new covalent bond. And quite often this is involved in what's known as a termination step. So we'll talk about what that means later on. So these are back and forth reactions. One other type of reaction you can do is addition to a pi bond. So let's say we have a radical X, and I've got this alkene, this is ethylene, and I want to form a new covalent bond between X and one of the carbons in ethylene. We know we can dump one electron over here, but to form a covalent bond, we need two electrons. So we'll steal one of the pi bond electrons. And then the remaining electron from that pi bond must go somewhere, so it'll hop over to that far carbon. So now we've made a new covalent bond between X and our carbon, but the last carbon right there now has an unpaired electron on it. Does that make sense? And then next, we have the reverse reaction that's just called elimination. And elimination is the exact same reaction of the addition to pi bond, but in reverse. So we've got that product we made above, but this time we're going to kick off X. So we're going to move one of these lone pairs, or sorry, one of the unpaired electrons over, steal one of the electrons from the sigma bond, and then the other electron from that sigma bond will get dumped onto X. So we end up making a new alkene because of that. Does that make sense? All right, and then there's a couple more. The next one we have is hydrogen abstraction. And hydrogen abstraction is relatively common. And that's where you have some sort of radical X, and then you've got a hydrogen coming off of some carbon chain. So I'll just abbreviate the carbon chain as R. And the whole idea is X, the radical, is going to steal the hydrogen that's right next to it. So in order to steal it, it's going to dump its electrons over, steal one of the sigma bond electrons, and then the remaining sigma bond electron will get dumped onto R. So now we've formed a new covalent bond between X and H. And then we've made a new carbon radical that I'll call R dot. And then last but not least, we've got halogen abstraction. And halogen abstraction is pretty similar to hydrogen abstraction, but we're obviously stealing a halogen instead. So for example, maybe you've got an R radical, you've got a halogen, I'll just call this XX, and it's going to steal one of these halogens, just like above, and dump off one of those sigma bond electrons onto X and recreate a new radical. So now we've created an alkyl halide and then a new halogen radical right there. One thing I will say is the halogens that we use are somewhat limited. X2 in this case, our halogen is chlorine, so Cl2, or bromine. You really don't see fluorine or iodine used in radical chemistry. The reason you don't see iodine used is it simply is too slow. It's not practical in any way, shape, or form. And then fluorine, on the other hand, is a little bit too excited to do radical chemistry. I remember hearing a story once about a guy doing radical fluorine chemistry, where he said, "I'll give you 3 reasons not to do radical fluorine chemistry," and he holds up the 3 remaining fingers on his hands. So radical fluorine chemistry is not done in most synthetic chemistry labs simply because it's a nightmare to control. The one we most commonly see is bromine because it's kind of in between being too unstable and too stable. It's kind of the Goldilocks effect there. So we will see bromine used heavily in this chapter. All right, so you can see this is pretty neat because in the first step of this reaction, we're taking a radical and then we're making a new alkyl halide. And then with alkyl halides, we can do SN2, SN1, E1, E2, things like that. So now we can actually make our own alkyl halides. I'll show you guys how to do the overall reaction mechanism for this, though. So halogenation of alkanes. And I'll show you a good trick before you get started with anything. And the trick is to identify the hydrogen that, if abstracted, would result in the most stable radical. Okay, so I'll give you an example one, and I want your guys' help with this. So let's say I've got this starting material. What would this be called? Not everybody all at once. Yep, methyl cyclohexane, right? The parent cyclohexane, we've got a methyl group coming off. It doesn't really matter if we number it as one methyl cyclohexane because that's assumed, right? Okay, so let's identify some protons. So for example, we've got protons here and here. I'll label these as red protons. They're symmetric, so they're going to behave very similarly, right? We also have a blue proton coming off this central carbon right there. And then we've got some green protons coming off right there. And if you wanted, you could even do the rest of the protons, but I'll give you a hint that it's got to be one of these 3. All right, so of these three different colored protons, which one do you think is going to result in the most stable carbon radical? The blue one, right? So in this step, I'd say if we lose this blue radical right there, so I'll do minus H dot. This results in a tertiary radical. We know that tertiary radicals are more stable than secondary, and they're more stable than primary, right? And do we have to worry about resonance here? No, in fact, there's no pi bonds. There's no opportunity to delocalize that at all. So this is the best option we have. And that gives us a good clue when we're doing the mechanism which hydrogen to abstract. You always want to abstract the hydrogen that will give you the most stable radical. All right, now we can get into the mechanistic details. And these radical reactions involve three distinct steps. The first one is initiation. The goal with initiation is just to create a radical from a non-radical. So for example, let's say I have bromine around, and I want to split it into two bromine radicals. We know the arrow pushing would look like this, where one electron goes over to one bromine, the second goes to the other bromine, and we end up with two bromine radicals. Bromine won't just do this on its own, though, right? It's normally pretty happy with that covalent bond. What do we need to break a bond? Some sort of energy, right? And the energy could be in a bunch of different forms, either heat energy or light energy, right? Usually with radical initiations of halogen, it's easiest just to apply UV light and heat to ensure that the thing actually works. So you can do heat, which I'll show with the delta symbol, and then the symbol for UV right below. So in order to do this, we just kind of crank up the heat, and usually you get a mercury lamp. One of the lines, one of the diffraction lines from a mercury lamp is actually in the UV region, and it will help split that bond in a homolytic fashion. All right, so that's initiation. We've made our radical. Step two, we need to propagate the radical. And anytime you propagate something like a plant, right, the goal is to take a plant and create a new plant from it. So we're going to take our radical and try to make a new radical out of it, right? That's the whole goal with propagation. And with propagation, we're going to take the radical and our starting material. So in this case, our starting material we said is methyl cyclohexane. We know the best proton to select is that one coming off the tertiary carbon. And we're going to do an abstraction here. So bromine is going to abstract this hydrogen. The second electron is going to go over and land on that tertiary carbon. So now we've got our tertiary radical. We've created HBr. But we're not quite done yet, right? We've got to regenerate our bromine radical in order for this to be a true propagation. So in the next step, you can assume that not all of your Br2 up here was split into radicals. Maybe it's only a small percentage of it that was actually initiated into a radical. So we'll assume that there's excess Br2 around. And that radical is actually going to steal one of these bromines. So it's going to reach down here, steal one of these bromines. So one of the sigma bond electrons will dump over, form a new covalent bond. The second one will be dumped over to the bromine right there. But the whole point with propagation is you need to regenerate your radical. All right. So at this point, we've created a alkyl halide. We can do E2 elimination, get our Hofmann product or Zaitsev product, depending on the base that we're using. We could do SN1 chemistry. Can we do SN2 chemistry on this? Not on this one. It's too hindered for an SN2 attack to take place. But now we've opened up the door to a huge amount of chemistry that we can do on these alkyl halides. All right, there's one last step, though. We don't want radicals just floating around willy-nilly. They'll do bad stuff. So we've got to get rid of them somehow. So the last step, step 3, is termination. And the whole goal with termination is to try to get rid of your radicals somehow. And there's actually 3 different options for termination. One option is, let's say you've got 2 bromine radicals floating around in solution. They can just find each other and form a new covalent bond and reform the bromine that we started with. So that's one option. Another option is maybe you've got this alkyl radical that we made before, and you've got some bromine radical floating around. It can actually form a small amount of your alkyl halide, which is good because that was what you're trying to make to begin with. The worst option that is somewhat unavoidable in some situations is if 2 alkyl radicals find each other and end up forming a new covalent bond. Whoops. And so usually when you do radical reactions, you end up with a trace amount of this impurity that's an unwanted byproduct of the reaction. Typically, when I ask you for a mechanism, though, you can pick any one of these 3 options. You can pick the top one, the middle one, or the bottom one. I just want to see that termination step where you're going from 2 radicals on the left-hand side to a non-radical on the right-hand side. So when you draw these mechanisms, make sure that you include all 3 of these steps. It's really tempting. I'll show you what's common up here. The students will just have a BR dot example, just terminate at that step, and they completely skip over the propagation. You want to show the full propagation step where you regenerate that BR dot radical, so don't try to take shortcuts there. Does that make sense? All right, so let's make a couple of notes here. If excess Br2 is present, it will continue to react. At next best site. So you do have to be somewhat careful with how much bromine you add. If you add in too much, you might get over halogenation, and you'll end up with multiple bromines coming off your starting material. So you do have to be very careful with the amount that you start out with. Does that make sense? I'll show you guys a cool reaction where they actually do this on purpose, where they add in an excess amount of their halogen. And this involves the natural gas industry. We've got CH4, that's methane gas, right? That's from natural gas wells. And what they do is they can react this with chlorine gas, and they do this in excess. And they do this using UV light. And with UV light, they can over-halogenate it, make carbon tetrachloride. That's an organic solvent that's kind of being phased out because it causes cancer. They can also end up with some of the trichlorinated product. This is called chloroform. Chloroform is a common organic chemistry solvent. The next one that they might get out is the dichlorinated product. This is dichloromethane. You guys have actually used that in lab. It's a really common organic chemistry solvent. And then they can also make chloromethane. So they can use this method to convert natural gas products into more useful alkylated products that can be used in chemistry labs. Basically, everything's derived from petroleum, though. So whether that's natural gas or some sort of hydrocarbon found in oil. All right, so let's take a look a little bit more. In this example, we were looking at chlorine rather than bromine. And I wanted to show you guys the problem with using chlorine. This has to do with regiochemistry. And I'll give you guys my kind of cheesy spiel. Chlorine is promiscuous. What does it mean if you're promiscuous? You're okay with more than one partner, right? It's not very faithful here. All right, so let's compare chlorine to bromine. Got chlorine up here, UV light, versus bromine down here with UV light. Where do you think the best site for halogenation is? Do you think it's going to be one of the methyl groups hanging off or the central carbon? Central carbon. And so with bromine, that's exactly what we observe. We get approximately 100% of the product right here. One could argue maybe, just maybe, you get a little bit of this. However, it's almost 0%, so you don't really have to worry about that. With chlorine, the story kind of changes a little bit. Chlorine doesn't care very much. It'll do either or. And in fact, when you look at this, it's only 72% of the product on the left, and then it's about 28% the product on the right. As a chemist, this is pretty unacceptable, right? And so usually chemists, when they're doing radical halogenation, prefer to use bromine because they have a lot more control over the reaction. And so let's briefly take a look at why this is the case. So I'm going to draw a little reaction coordinate diagram down here. You guys thought you were done with these. All right, so if we think about our radical starting materials, right? Do you think the chlorine radical or the bromine radical will be more stable? What do you guys think? Bromine, why? It's a larger atom, right? Larger atoms have a larger electron cloud for that unpaired electron to be in. So bromine radical will be this lower energy step. Chlorine will be the higher energy step. Both of them have roughly the same transition state energy. So for example, I'll do the chlorine as a green pathway. And we're trying to go to the same product down here. Versus the blue pathway for chlorine right here. And then where do you think fluorine would be if we tried to do fluorine? It'd be even higher, right? So I'd say, all right, fluorine, if we were brave enough, would be up here. And I'll do a red pathway for fluorine, but we know that logically this is pretty dangerous to carry out. So if we look at this, the activation energy for radical fluorination is incredibly small. So small that it becomes a problem, right? It'll start doing chemistry before you want it to. The chlorine one, like I said, is that Goldilocks effect where it's in the middle. But because it's higher energy, it's still going to be less picky than bromine. Bromine's the most picky of them all. And then iodine, on the other hand, just doesn't really like forming radicals. So it really has to do with the activation energy of these. Bromine has a large enough activation energy for us to be able to control it, where with chlorine, it's a little harder to control because the activation energy is lower. All right, so one last thing before we continue on. We've talked about regiochemistry. We've got to talk about stereochemistry now. If we look at our last reaction, sorry, I'm going to scroll back up again. Our product that we made here, we didn't have to worry about stereochemistry, right? Because we have no stereocenters. There will be occasions where we will form stereocenters. So let's take a look at what that'll look like. And let's do this with an example. So let's do Br2 and UV light. What product or products will we get out of this? Make this worth 4 points. Like I said, before you begin, identify the hydrogen that's most likely to be abstracted. Which hydrogen do you think is most likely to be abstracted? The tertiary one, right? So we know that bromine is going to end up attached to that position. We don't have to worry about the mechanism right now, but we'll go through it in a second. So if we think about it, right, that bromine could be attached as either a dash or a wedge, similar to when you add into a carbocation. So this would be one product. Second product, maybe the bromine came in from the top face. And what's the relationship between these? Are they diastereomers, enantiomers, constitutional isomers? Enantiomers, right? And in this case, we'd get a racemic mixture of enantiomers. We'd get a perfect 50-50 mixture. All right, so let's really quickly take a look at this reaction mechanism. We'll try to go through it. What's step one? Initiation, right? So we've got to form our radical. And in this case, we can start the initiation step by treating bromine with some sort of UV light. So we'll kick one electron over to each bromine. Make 2 bromine radicals. What's step 2? Propagation. So we can take one of those bromine radicals that we formed before, and we're going to react this with our alkyl halide. Our alkane. And we know the first step is going to be a abstraction of the best proton. Oops, let me clean this up a bit. So we've made HBr and our radical. And we know that this is trigonal planar, so I'm just going to make a note. All right, and then step 2 of our propagation is a halogen abstraction. So this radical can steal a bromine from any excess bromine that's around in solution, and then kick off another bromine radical. And that can happen from either the top face or the bottom face. So it's a good idea to draw both of them. Or if you want to do this faster, you can just write plus En after you draw one of them, right? But the key is regenerating this bromine radical in the propagation step. All right, what's our last step again? Termination. So you can pick one of the 3 options. I always pick the easy one. I just do Br dot with Br dot and do a radical coupling to regenerate our bromine radical. It doesn't matter which one you select. If you want to pick the easy one, you're more than welcome to. If you want to pick all 3 and be super thorough, you can too. I'll leave it entirely up to you. All right, I think that's where we're going to end off today. Tomorrow when we come in, we'll talk about allylic bromination, which is pretty similar, but it does involve more resonance.